Thanks very much, Carlos. And we're going to give a quick 40 minutes on FUNcube progress over the last year. Is that not working? It needs to be on. Okay. Is that better? Yeah, good. There are about 5 or 6 of us, so we've each got a 5-minute slot. So we're going to sort of press on a bit. If we do overrun, we have got a script, but if we do overrun or likely to overrun, then we'll just stop it and we'll slot the remainder of it in another sort of session. It's not a very highly rehearsed presentation. Shut up! I just, by way of introduction, I wanted, when this was put about, the FUNcube project, largely by Graham, over a year ago, we did this paper for the RCF to get the funding. I thought, this is something I want to be involved in because it's exciting. At least I think it's exciting, it's fun. And unfortunately for me, and perhaps fortunately for the rest of the team, my technical knowledge is not huge. And I thought, what role can I sort of suggest I do that doesn't require technical knowledge? And I thought, and I said to Graham in a phone call, I said, look, I'll be the project manager then. And my experience of project managing is limited to the Ministry of Defence, where I had a job as a project manager in the procurement executive about 20 years ago. But it's taking a different style of project management, this, because in the MOD days, you sort of phoned up a contractor and you could bribe them with money and stuff like this. With a current project team, you have to bribe them with wine and tricks and stuff like that. So I had to change my tactics slightly, and I'm very grateful to the team, most of who you will see, not everybody, but there was a slide with a list on them, for putting up with my slightly abstruse questions on occasions and being patient with me. So that's my role. Let's just go through these slides. This is how we started off about a year ago, and I won't read it out. Some of you have seen it before, but the primary objective was for science and education, and a bit like Barry's mentioned, that will sort of sell it to the public. And we've got a second objective is for an amateur radio transponder. And this was our proposal about a year ago. And again, I won't read it out. Notice the material science experiment at the bottom, which I don't think we're going to say an awful lot about, but David Bowman's the expert on that. We had an argument, we didn't have an argument, we had a meaningful discussion last year about what's a computer and what's a programmable thing, but we won't go there this time. This is our logo, which we sort of invented some time ago, and it's intended to represent a child and an adult, different sexes, you'll notice, so we're trying to include as many people as possible gazing into space, and our sort of strap line is fun in space with amateur radio, because we feel that gets the amateur radio in, it gets the space in, and so that's that. This is where we've ended up after a fairly general statement before, and it's pretty similar. One new CubeSat, quite a lot of off-the-shelf stuff. We are signed up with a contract with ISIS BV in Holland, and they're actually doing a lot of it, the structure, the EPS, solar panels, and that sort of thing. 2 dipole antennas. What I think is a pretty novel, and you hear about it more, sort of downlink with FEC and all that. OBC we've covered, UV linear transponder. We've got 30 plus telemetry channels, including whole orbit data. And we feel that's important, a lot of telemetry for school children to literally play and experiment with. And we've invented a new term called FITTER, so you have to think Twitter for this. And these are FITTER messages for FUNcube. They are a bit longer than the Twitter messages, they're 200 characters long, and we have 9 slots essentially available on the satellite, and they get broadcast. You'll hear a bit more about this later on, but they get broadcast. I think they go around once every about 3 minutes, I think, isn't it? Something like that. Okay. You certainly, if you listen to about a 5-minute pass, you should be able to receive all of the fitter messages. That was the sort of the deal. And the idea of this is that we, the ground station control stations, can upload a message which might be welcome to the XYZ school field day or sports day or something like that. Then the kids can receive it. There are other possibilities as well. There's the block diagram, which none of you can read. Can you? No, maybe in the front row. So we've got a block diagram anyway, and it's got all the sort of traditional things. So I won't spend any more time unless you think I ought to on that, because I want to press on a bit. This is just a drawing of what it's going to, an engineering drawing, just to show we've got our documentation right. The antenna deployer thing, which is a drawing top left, looking down on the Z-axis. There is an actual one in the shop for you to have a look at. This is the technical team. I should say there are others involved, but slightly more on the periphery or slightly less active than the names you see down there. For various reasons, commitment reasons. There's one guy who's been quite seriously ill, well actually two, come to think of it. And we have regular meetings on Skype on Sundays and talk over what we're doing and update each other on our progress. We bought an engineering model, again in the shop. You'll see a little thing that is rotating around is a structure, and we bought an EPS as well because we felt we needed that too in the early stages to test against. And these two pictures are taken at our first face-to-face meeting. This is the agenda. Wouter is in charge of designing these are all AMSAT contributions to it. So over and above the ISIS stuff that I mentioned, these are AMSAT contributions. Wouter will do a bit on the RF board. Davey will do the PA board, the CCT board, command control and telemetry board. Michael has got a script because none of the CCT board team, which are 3, can make it today. So don't treat him gently. The receiver, Howard, is going to do the ground station receiver. Howard's going to cover, and Dave is going to do a bit about the ground station GIU. So, over to Wouter. Of course.
Right, I will probably hold it like this because otherwise switching will take longer and longer. I only have 3 slides about the RF board. The main function of the RF board is going to be providing the RF downlink signal and providing an uplink capability, so we can actually send stuff to FUNcube and use the transponder. It's a design based on Delphi C3. I was involved in the Delphi C3 board design. Had quite some talks about it, and also here I did some presentations on the RF board, or at least the Delphi C3 transponder boards. But just to recap, I have some of the block diagrams. Again, maybe not that readable in the back, but I will go quickly through it. There was a laser pointer somewhere here. This is the receiver board block diagram. Over here you have a UHF input with some ESD protection to keep static from building up on the antennas, with a filter, front end filter, and an LNA, and again a filter. So this is actually the 70 centimeter uplink LNA path. Then we have a mixer which mixes down the signal to IF of 70 megahertz, and the local oscillator for that, which is a crystal oscillator. After that, 70 megahertz is amplified with the IF amplifier and fed to a bandpass filter again. And another conversion step mixes that down to 10.7 megahertz. And here the interesting part happens, because here we split off the transponder signal this way, 10.7 IF, and we have the command radio uplink decoder behind it, and it has some filtering and an additional mixer step. This is actually inside largely inside a chip from Motorola, FM receiver chip, this part is 10.7 megahertz output. which goes to the transponder circuit, and yeah, the telemetry or the uplink data here goes to the CCT board, the computer control board, which processes any commands and receives all the data, for instance the upload of a fitter message or a mode switch or anything we want to do to command it. Then we have the TX, the transmitter. Essentially that transponder chain goes in here. I forgot the arrow I see now. So the 10.7 IF of the transponder goes in, gets filtered and gets amplified, 40 dBs over here. And then we have a AGC chip to actually act as the AGC on the transponder. This is a sort of plain AGC, so it's not something divided in channels like the more advanced transceivers or even the software-defined transceiver, in which you can have actually channels and do something with that AGC, that one channel. This is for the entire passband, so the loudest signal will will actually determine well, what comes through at what level. Well, there's a downside, but this keeps it simple. The forward power of the transmitter is used as input, so it's regulated around the PA as well. So if there's any deviations in, for instance, driver stages or PA gain, it will also correct for that. After the AGC, it goes into a filter again and gets combined at 10.7 megahertz with another signal path, and that's the telemetry path, in which we can modulate telemetry from the CCT board, so yeah, values for various temperatures and currents and other interesting bits, which goes, it's modulated by a double balance mixer, which makes the BPSK signal for FUNcube, just like in Delphi C3. It's also a 10.7 megahertz signal, which is combined with the transponder, and then goes to an up mixer to get it at VHF 2 meter signal. So we directly convert it up, filter it and amplify it, and then it goes to the PA board of David, which actually does the final amplification. And one of the actual, of the things we left out in Delphi C3 because of time problems, we now have in is a loopback mode, and that's an additional mode we did, inspired by AO16, which had a way of looping back the FM command receiver signal, the demodulated signal, back to the modulator of the downlink, and we did the same thing. So now it has that loopback mode, so you can actually do a AO16 like loopback. So that's in a nutshell the transmitter and the receiver of FUNcube. Not in the block diagram, I put power conditioning, an I2C ADC for telemetry collection, a temperature sensor, and some current sensors. That's to keep this talk a bit quick because there's other boards, and I would like to invite David for the PA board talk after the output of the RF board. There you go.
Okay, thank you very much, Walter. Okay, so about halfway through this project, we suddenly discovered that even although we were working with a CubeSat format, we had enough space to allow us to separate out the RF amplifier from the rest of the RF board. And we thought this would be a good idea, as the last thing you wanted to do was have stability issues on a very closely packed RF board later on in the project and then have no way to cure them. So we had extra space, so we've separated out a fairly simple part of the circuitry. This is essentially the heart of the 2 meter amplifier. Remember, this is mode UV. So we have a final amplifier centered around a Mitsubishi surface mount FET. The FET is working in class AB1, So hopefully when there are no users of the transponder, we'll be able to get a bit of extra charge into the CubeSat batteries. Essentially this is a very simple PA. Almost this comes straight out of an application note from Mitsubishi. However, if I can pass this board around, if you can hold it by the sides please. This is one of the PA boards we've had produced. This however is only a small fraction of what's actually on the board. If we go through to the full circuit diagram of this, you can see the amplifier actually occupies a fairly small area, and all the rest of this is to do with telemetry gathering points. So along with our amplifier, we've got an output power coming from here into a low-pass filter. The low-pass filter, of course, in this case has to have very good performance for rejecting the third harmonic. Remember, this is operating at 145. The receiver on board FUNcube is operating up at 70 sems. And of course, the third harmonic of 145 actually falls at 70 centimeters. So we have a great potential here for creating interference to our own receiver. So we've got a couple of traps in here at the third harmonic. And simulating this, we get ludicrously over-optimistic figures of slightly over 100 dB of rejection at 70 sems. Of course, in real life, the signal will jump across the filter. And if you have a look at the board there, you should see that we've allowed enough space around it to add additional shielding, so we can increase the performance if we need to. Looking around the rest of the circuit, the rest of it's associated with telemetry gathering. Up here we've got a supply line which comes from the battery bus, so anywhere between 6 and about 8.2 volts off of some lithium-ion cells. A couple of current sense resistors. Notice we've got two in parallel there to avoid single point failures, so one can crack. That'll affect the accuracy of the telemetry, but it won't actually stop the thing dead in its tracks. So we have some redundancy there. An amplifier amplifies the 30 to 50 millivolts we're expecting from this point up into a voltage, and that's available for telemetry. The RF output power at the end of the RF amplifier comes down to here, which is a bidirectional coupler from mini circuits. That senses forward power and reverse power. We have a couple of little resistive pads here before some analog devices, power detectors, again converting the RF into an output voltage. And these two are available for telemetry gathering. So the telemetry signal of forward power comes up here, and reverse power from the reverse power detector also comes up to this device. Fourth and final input for telemetry comes from a PA temperature sensor, so just a thermistor mounted across the device, and that provides again an input to this analog to digital converter. If you have a look at the board as it comes around, this is a very nice device from Maxim. It has 8 pins, so it looks like just a very small operational amplifier style package. But one row of pins from 1 to 4 on one side of the device are analog inputs. The device outputs that data on an I2C bus, which means that these two lines are commoned right the way through the satellite, and this individual device or other devices like it can be addressed by the processor, and those items of telemetry picked out and then formatted into the telemetry stream. Final little bit down here is just switching, just so that we can interface the board to the command and control system. After a little while, we realized that there was one additional benefit of using an FET here. Anyone who's looked at FETs in space might know that one of the characteristics is that their bias point tends to drift as they're exposed to radiation. In fact, they're used for estimation of total dose of radiation in space projects. We realized that if we could remove the input from here and measure the bias current, one of the other things we could do over a long period of time is estimate the amount of radiation that's falling on that device in terms of the bias drift. Hopefully it won't drift too far to actually short out the power supply lines, but we're expecting to see a small amount of drift in bias over the lifetime of the satellite, which will give us an indication of total dose that the thing's been exposed to. Okay, last slide from me. That's a picture of the PCB which is coming around. Simply RF in at one side, the amplifier goes in here, lots of filtering with traps, directional coupler down at the bottom. Incidentally, ITAR got me on that one. I placed the order for these things in about May. Foolishly told them what it was for, and ever since that I've been filling out paperwork. They're due in about 2 weeks' time. And then these various samples come up to this device here, which is the Maxim, I think it's the 11607, with the 2 lines out going to I2C data and I2C clock, and that also picks up data from all other parts of the spacecraft. Okay, that's it from me. I wonder who's next.
Good afternoon. Can you hear me? Yep. I'm going to talk about the CCT board, and I might as well show it to you first. It's the only sample at the moment, so I don't want to zap it with ESD. So as you can see, it's much simpler than the RF and the PA boards that you can see from the back. And I'll just draw a quick schematic. It won't be quite as complicated as the previous schematics. It's MCU, CPLD. That's it. Perhaps I should draw a few lines there, but that's basically it. Nice and simple. The reason we made it simple is that we don't want it to go wrong. So the idea of it is that the CPLD is the fallback. So CPLD is the configurable programmable logic device. Basically, it's a bunch of logic all in one chip. So it's the chip on that board there. And then the MCU does the telemetry, creates the telemetry, gets the data off the other modules, and creates the telemetry packets. So I'll go through the CPLD first. As I said, it mops up all the logic, so it's a glue logic in effect. And it also has a digital to analog converter. We've been touching the board. It makes you crouch down, does it? So the CPLD really doesn't do very much. It's also got a watchdog as well, so that if the main processor flunks out because of space, then the CPLD will keep things going. Obviously, there'll be no telemetry, but it will keep the basic transponder running. The other part is the processor. It's a Freescale 8-bit processor, and it was chosen primarily because of the low power. So an 8-bit processor usually are much lower power than a 32-bit processor, and a bit more proven in space than the 32-bit processors. The processor can't be updated in space, so it's basically you load the program in, and that's the last chance you're ever going to see it. You can't update it. So the processor has got an I2C bus on it, so it can receive the data, the telemetry data from the EPS and the RF board and the PA board, and then it will create the packets and add on an FEC, so a forward error correction. So basically the format follows Phil Kahn's protocol as described on the ARISAT. So the only difference is that we're running at 1,200 rather than 1,000 bits per second. So that really covers the MCU board. The idea of choosing an FEC or having an FEC is that we can improve the bit error rate, so that either you receive the data or you don't see anything at all. So that's the improvement you get. Rather than a few bit errors every now and then, it basically all comes in and it's all corrected. So any errors are cut out. So overall, what we were looking at in the design was we needed to work over a normal temperature range, an industrial temperature range of -40 to +85. So nothing too exotic. Low Earth orbit is fairly benign compared to some of the other orbits. Another consideration was we didn't want it to be too heavy, so we didn't want components vibrating off during the launch, and most important of all was low power. That's the telemetry board.
I'm just going to interrupt you a minute. I'm just negotiating with Howard. I'm just going to skip over his bit for now, but you're going to do it immediately after tea. So, they will be months, yeah?
Back to my notes.
Thank you. Good afternoon. I'm Dave Johnson, G4DPZ, yet another volunteer for this project. I come to this with a software engineering background. I've done sort of tracking systems before now, and in the past I did some work on Sat1315 for its use on the space station. What do we mean by the Groundstation GUI? Well, there's two parts to it, which I'm going to explain. I'm going to explain how we're going to implement it, when's it going to be available, hopefully a long time before the satellite's ready, and who can use it. To those of you who know Delphi C3 very well, this is Rascal, the application that's used to capture the data. We have the idea that the school user will use something very, very similar to this, except it'll be our telemetry. One thing we have to consider is user authentication. We have to be able to register who the user is, in terms of if it's a school, what the registration number of the school is, in terms of the sort of education authority, so we can capture the information and maybe put them into some sort of scoring scheme of how much telemetry they've collected. We have to do data capture. It's the telemetry coming down from the system. Just made some quick notes. A full set of telemetry is about 24 frames of data, 12 of which are real-time, 4 are high resolution, and 8 are fitter messages. I think that makes 12. That makes 24. With each packet, we actually send real-time telemetry for the materials science system. Data transport, we have to have a mechanism for transmitting the data from the ground station to what we're calling the data warehouse. Now, the data warehouse will be where the analysis can be done on the web. That's one difference to what Rascal did. We're actually going to make our information public. And the data analysis mechanism, the idea being that if we can identify the user, they can actually recover their information from the web and do the analysis on it. And there'll be a general analysis mechanism too. Implementation, quite a few things to consider. I did work for the Department for Children's Schools and Families last year. They are very cognizant of schools' information and where it is at any point. We can only store the bare minimum of information. One thing that we did consider when we're talking about the ground station and the warehouse is where to store it. You can get very cheap storage from places like from Google, but that takes the information offshore. We're not allowed to do that, so the information has to remain onshore. Network availability. In schools, it's unlikely that we'll get the ability to talk anything other than on a HTTP port. Port 80 or port 443 for secure mechanisms. So we have to make sure that whatever we do is compatible with school network systems. Online, offline operation. It could possibly be that a school's in a scenario where they don't have permanent internet access, but they still want to be able to use the ground station. We've got to be able to allow for the storage of information within files, and then upload files to the system, rather than real-time ops. Performance, we're not talking about high bandwidth. We can get away with normal, a modem, I say a modem. A 3G dongle will do it quite happily. Data volumes, I think for the whole lifetime of the project, I think we're probably only talking about 20 gigabytes altogether. It's a tiny amount of data. We're not talking terabytes, so we're not worried about large volume storage. Display, you've seen the Rascal description before. There will also be a web version done in such a way we can just display the raw information, analysed information, school-specific information. We've also got to consider what the development skills of the team are. Well, I've done something like 30 years of IT in terms of Groundstation and web, so that comes out of the box. Tools, my company are providing some of our development toolkits free for nothing, and there's a set of libraries because it will be predominantly an open source solution for the libraries particularly. We can get those available off the internet. When can we have the ground station? Long before it's launched. With PCSat-2, I was asked to do the website about 2 weeks before launch. It was a bit tight, but it went. It was ready. It was ready for when the astronauts turned the device on. Telemetry specs are done. I'm sure they'll be subject to change before launch, but we've done it designing in such a way that it's flexible. Transport protocols have been defined. It comes down as binary eventually from the satellite. That ends up with huge long strings of binary, which we can handle, but it's easy to actually do with hexadecimal. So we've worked out a hexadecimal protocol. Transport mechanisms, because we'd be shipping stuff across the web, we've got to do it over HTTP, the mechanism for the web. That's been prototyped and tested, so I have a mechanism for generating simulated data in the protocol, in the hex protocol we've defined. My service can pick it up and decode it as well. That's all been done for all 24 frame types. Source code repository, we need to store it as I make changes and I'll be able to back out just in case I've made a mistake. That's all in place now. User interface design is underway. Very early stages yet. The main thing is make sure we can decode the data. And I'm writing some simulation software. It's fine generating loads and loads of random bits. It doesn't make a lot of sense. So I'm actually generating some simulation software so we can actually model the orbit and model illumination and discharge, etc. I think that's me done. Okay, thank you. Something's reading ahead of me. Right. Who are the users? System administrators. We need to be able to manage the data within the system. We have educational outreach. We need to be able to allow teachers, lecturers, etc., to build material around the information we have within the warehouse. Students themselves, they need to be able to download the information they've uploaded by the ground station and do analysis on their own data. We can do it for them, but it's nice as part of educational exercises. I should really sort of roll the last three into one. Data contributors, radio amateurs, you guys, we're going to be distributing the ground station in the same way that Rascal was done, and we would very much like it to be used and give us as much data as we can possibly get. We're looking for whole orbit data and real-time data from you guys. And anonymous users, these are people who come into the website and looking to see what we're doing. It's great to see that AMSAT is doing a similar sort of thing, so I'm sure there'll be some synergy between us talking to you guys about similar sort of thing. That's it. Thank you.
We've got more, but in fairness to the other speakers, I think we'll just sort of break off here. Is that all right, Graham? And we'll pick it up after tea, when there's a bit more on the ground station and a bit more on outreach and STEM. Just to wind this bit up, it's quite a convenient place to start. We haven't pushed. We're going to need sponsorship. We've got money for the building the satellite. What we haven't got is money, unless we raid virtually totally the AMSAT-UK reserves. We will need money for the launch, and we haven't identified a launch yet. We've got a favourite launch, which has sort of got to the stage of expression of interest, but we haven't signed up for it yet. But when we do, the normal sort of things will you'll be hit with sort of pleas for sponsorship and of various sort of sorts. So I think that's probably where we'll leave it. We'll take a break. Do you want to say?
I'll just add one bit.
Yeah.
Sorry, Jim. Just realised that we've been so close to it. One of the vital bits that we've not mentioned so far is the fact that we've got a transponder and a BPSK telemetry stream. And the plan is that the satellite will, when it's in daylight, will be in telemetry only, high power. High power is relative, somewhere approaching half a watt of RF. The transponder will be switched off. When it's in darkness, when we assume that schools are not at school, then the transponder will function. So it will be very reliable. Transponder in the evening at night, or when the satellite's in night time. When the satellite's in sunlight, it will be telemetry only. When the transponder is running, the telemetry will still be there, but something like 10 dB or 12 dB weaker. So you'd need probably a proper aerial, radio amateur type aerial, rather than whatever is going to be necessary to receive the telemetry, which will not be very much in terms of antennas. Of course, we need some flexibility, like holiday periods or weekends, when again we believe that schools don't function generally, and therefore we will be able to command it on into amateur mode 24/7 for a weekend or over Christmas or over Easter or whatever. So we will have some control over that. But generally, it's telemetry in the day and radio amateurs in the evening. Yeah.
I think it's important to put on the website and live information. What the satellite is doing now. Is it doing telemetry?
Good point. So I just wanted to get that point across, because we'd forgotten it.
Yeah. Okay.
We knew it, but we'd forgotten it.
I won't take any questions just now unless there are any burning issues, but we'll be back later. Thanks very much.